Good afternoon, everyone. Thank y'all for having us from the Lone Star State. Today, we're going to be talking about, drilling in Salina formation, some of our, engineering field experience for both Pat and I. We'll be looking at asset identification, talking about some of the, geological perspectives of what you should be looking for and considerations and how that's going to look on your risk matrix. We'll also be looking at the intent of use as far as what that cavern will be used for, as far as like solution mining, disposal assets, and things to consider with the development of that project. You'll be looking into the future. Everyone either has an exit strategy or an overall plan for their facility and what they should be doing moving forward. And we'll talk about how your current operations could be impacted by those offset from you, such as oil and gas operations or disposal assets. And we'll highlight or just kind of discuss, current and future environmental issues that could come, at least what we've seen in the States from my perspective. Pat may be able to add in some color for the Canadian portion of it. We'll start talking about, total depths in your operating parameters and how some of that can be affected in what we see as far as the storage side, eliminating, roof falls, certain complications in that and what it means for your wellhead and your casing design. And we'll go from there to high-level discussions on drilling fluid, cement considerations, as far as like what you should be designing for in your parameters, and long-term your wellbore profiles as far as directional drilling and what realistic expectations are. After that, we'll highlight some of the stuff we've experienced or highlighted during our past experience on operations. A lot of our examples and kind of the talking points we're going to discuss today are going to be over active projects that go as far as the Northeast Basin and extend down into, West Virginia and the southern portions of it. And at the end, we'll kind of wrap up with a drilling example of some of the complications that occur, at least what we typically see drilling in salt. There's historically a lack of data due to the minimal amount of drilling or activity in that space. And looking long term, if you're able to mitigate that and spend the money up front to resolve some of these issues, how it can help accelerate operations and lower your overall investment. So as Pat highlighted, my name is Colton Long. I've been with Lonquist since 2021, graduated from Texas A&M University as a petroleum engineer in 2019. I started my career highlight during COVID with Chevron. I was part of their drilling completions team in the Delaware Basin. In 2020, we drilled 240 wells, primarily targeting Third Bone Springs. So data and analytics and really driving down efficiencies and margins is a resource play is your primary function. I've tried to bring that over to the salt side. And since joining Lonquist, primarily been focused on UIC assets with disposal wells, class 1, 2, 3, 5, and 6. We also have Patrick Seymour. He started his career with Apache doing well site supervisor in the Alberta Western Province. Since then, spent 11 years as a drilling superintendent for Husky Energy. He's been able to come over to Lonquist in 2017, also bringing over some of that operational and engineering experience to try to help optimize design and operations. So asset identification. One thing that we see, at least from my experience looking in the Gulf Coast, is how things are going to be used either for solution mining assets, gas, liquid storage, and disposal well assets. But like class 1, some of the stuff we've seen, industrial, hazardous, and non-hazardous waste. Some of these assets were drilled a long, long time ago. We're looking at assets that are still in operation for disposal and solution mining from the 50s and 60s. And along with that, practices have come a long way for the use of pad fluids, casing design, and what have you, and even like current upgrades to liquid and gas storage assets. And since 2008, most recent, or I guess the heavy 2008-2014 downturn in the gas market, that lull in production on the oil and gas side really has brought about a need for storage, which is bringing back a huge emphasis and investment in the UIC classifications. Moving from there, securing key acreage. So one thing I'd mentioned earlier, if you look at all of your stuff, like I said, you've got assets in place that primarily where we're working are focused around petrochemical plants, solution mining services that are used for agriculture products, single-use plastics. And one thing most of those places have in common, at least in the States, is they were developed before the Endangered Species Act, Water Rights Act, etc. A lot of these facilities have been in operation since 1970. One thing all these places have in common is urban encroachment. These were built along water paths. ports, ways of transport. Well, during that, you've had housing development and increased industrial development around you that has kind of pinched off access to what I would say is a very small part of these companies' portfolios, but ultimately can be a massive valve that can shut down the entire operation. Just because the well goes down for a petrochemical plant like Exxon doesn't mean they can shut down their facility. They're still producing waste that must be handled in an appropriate manner. So securing key acreage, looking ahead, long-term planning. We're currently helping a company right now, which you'll see highlighted on the next few slides, that the facility has been in operation since 1914, since World War I. They've had several different caverns and galleries developed over the years, and one thing they're running into now that they never thought is, hey, we've got 10 or 15,000 acres to develop. We should have all the space in the world we need. And because of lack of planning, there's a realistic possibility in the next 3 to 5 years that the facility is going to have diminished capacity on production, or ultimately be led to shutting down parts of the plant just because they have nowhere else to go. So, and then also you'll see later in the presentation, adequate spacing, which in oil and gas has plagued people for years, being either too over-optimistically a resource in play, or spacing too tight and taking frac hits from one another and ultimately eroding value capital. And then as far as like current and future environmental regulatory issues, like I said, a lot of these areas are focused in ports, riverways. For solution mining assets, this can be a blessing and a curse. You can get your product to market easier, but if something goes wrong with your well and you have loss of containment, you actually have a perfect storm where you pollute the bay, you send brackish or brine water down a river system that is maybe wetlands habitat for waterfowl life or other aquatics. And beyond that, a lot of the stuff we see that we'll discuss on the wellhead side, non-API equipment, most of these assets are managed what I would describe as surface facility folks. A lot of that fall back onto ANSI requirements, not having 2 barriers per API recommendation, etc. So as discussed, here's one of the projects we're currently working on. This is a deeper asset with the Salina Salt, averaging between 6,800 feet, 2,000, 2,500 meters, and I guess another 200 or 300 meters deeper in parts as it dips. This is an image from 2010 that I created in Drilling Info, kind of shows and highlights the oil and gas development around them. Historically, oil and gas development in this area was shallower than the Salina Salt this depth, typically ranging either above the Marcellus, Queenston, Onondaga. What we're going to see here, since the shale revolution came around, it's opened up new resource plays that are actually deeper. And the issue that this facility has ran into is they're getting blocked access in the states you have, as highlighted earlier, pore space rights and mineral rights. They're actually having some of their access cut off because of oil and gas development around them through the deeper zones. So 2010, we'll jump forward 5 years, another 5 years to 2020. And here's what it currently looks like in this isolated area, with the blue wells being their facility. In the next 3 to 5 years, this facility has the realistic possibility either of having to uproot and develop an entire new field much further away from their hub of operation, or potentially being shut down at some point just due to excess minerals. Another example, this is a shallower part of the Salina up in Ohio. This is about 3,000 feet, so I'm gonna guess 1,000 meters-ish. So they built this facility, this one's probably 1940, 1930, and the town's just grown up around it. And there is nowhere else to go for this facility long-term. They've mined up most of their resources in the area. They have maybe 5 or 6 well spacing to come into play, but they're already having, I would say, combatants or issues with local municipalities as far as operations and working parameters. So far as like drilling, completion, engineering design, one thing I've kind of been pushing operators to do historically on these solution mining facilities in the Salina, a lot of this has been low pressure gradients, and for good reason. If I can put cheaper pipe in the ground, cheaper facilities, it quote unquote can be safer. But there's also at times where it can also be creating long-term damage to your asset. So when working with the facilities groups, there's benefits to operating at higher pressures, and most of that's going to be driven on what they can handle coming into their plant. I'm not saying every facility needs to have a 2 to 3, 4, 5,000 PSI wellhead or casing set system. But being able to operate at higher pressures will help reduce roof falls. There's direct correlations with lateral extent of mining in vertical resolution or even in your horizontal drilling applications. And then moving that forward, we've seen some of these facilities, mostly historic, that also have failure to implement automation. Most of this is very much hand-turned valves. So being able to automate that process, track data far as their saturation rates, what they're getting back at surface, because this really needs to be dialed into energy in, energy out equation. From there, we can move forward with the casing design. Most of these facilities, oil and gas casing specs will overwhelmingly meet what y'all are requiring. But as you move into the higher operating pressures, you enable yourself, as far as casing design, to later, flip this asset for gas storage. A lot of the solution mining guys are only worried about, hey, I only want to get my salt out now, my resource now for disposal. If you take the time and set it up front, welding your production case string goes in. That's a simple thing you can do. It seems like a lot of money up front, but now you've enabled yourself to operate in gas storage applications, which greatly improves the upside if you ever need to flip it or have rental rates going on for firm storage. Whenever designing your casing design, I've seen some very precarious ways of designing it that have evolved, I would say, on this side of the industry as a whole. I would redirect everyone back to API standards as far as like tensile burst collapse ratios. With the upside, if any string set in salt, I would increase the safety factor as recommended. And I'm not as sure in the Ontario region if this applies. In West Texas, where we have the Salina Salt development, one thing that we're having to worry about is shallow injection zones up above where high corrosives or corrosive environments have been created over years and years of injection with high H2S content. After that, being realistic at data up front, I know there's not as much development opportunity. You're typically doing one off, two off, maybe, multi-well or multi-pad drills occasionally. But I would really push operators to say, hey, figure out your pore pressure on the initial well, spend it, or initial couple wells, spend the money a few times to figure out your pore pressure. That way you can degrade your casing design, your operating pressures, and have a better understanding of potentially which way this salt's going to mine. That way you stay within your preferential rights. From there, once you gather all that data, future wellhead, future casing designs, you start moving to cost savings where you have tapered strings, lowering your casing weights. You can start setting intermediate liners, reducing the number of strings you have to cement to surface, etc., and logging liability for open hole logs. Jumping into wellhead design, a lot of stuff we see, at least in the States, like I said, historical production. So it was set with a conventional wellhead system where you're using slips, compression to really activate those seals and provide your isolation. In certain parts of the country, especially certain parts of Texas where the salt is extremely shallow, you typically don't have enough weight to keep those activated and sealed in your system. And what we see 90% of the time is they got a bull plug in there, and they do not have an effective braid head monitoring program in place to track gas migration of fluids potentially into your base of usable water. So I would say, making sure you have the right tool for the right application. For single-use wells or a one-off well, conventional slips are fine. Make sure your casing in your wellhead program is set up to stay activated. Make sure you have an H plate on top. If you're going to do any type of batch drilling, one thing I'd recommend people really move to is multi-bowl systems. It eliminates, there's a lot of cost savings there. You don't have to break your stack anytime. You land your bowl on the different load shoulders. You go ahead and start running the hole you drill out. You're waiting on cement after that point. I would say between conventional slip set and a multi-bowl system, you're saving 24 to 36 hours per casing side. So, yeah.
Okay, so I'll get into a little bit more specifics, I guess, on the drilling mud and cement for the actual drills there. So basically, surface hole intermediate sections are the same as we would use for conventional drilling, just, water-based systems. Basically, just drill with water, let your cuttings build viscosity. Basically, here we can't use salt systems because we need to protect that base groundwater, so our drinkable groundwater, usable groundwater. But when we get down to the target interval, so anytime we're in the salt, we need to then use a salt-saturated system. So this is a completely saturated system. Basically, our goal here is anytime we're in that salt, we can't be using water. We can't be mining that salt. So we'll either use a salt system, or we have used invert systems in the past. One benefit we saw with the invert systems is in our core recovery. So anytime we're taking cores. We're basically invert system helps guarantee we're going to get 100% core recovery there. But for the most part, if we're not coring, we're using a salt saturated brine system. For the cement, it's kind of the same principle where for surface, we're just using a regular Class A cement. One thing here, just making sure we're using 100% excess. We need to make sure we get cement returns to surface, protect that groundwater. Then again, in that salt interval, we need to make sure we're using a salt saturated cement, so we're not washing out during the cement job. We also, one of the things we've seen in a lot of our wells here, we use an annular casing packer to provide a mechanical barrier in place of, along with the cement shoe. So we'll just set that annular casing packer and then use a stage EV or stage tool above that, circulate cement above. We need to make sure we're waiting on cement to set up over the 500 PSI prior to drilling out, and then we run our cement bond logs and temp logs to confirm the quality of the job. Wellbore profiles, so the salt wells we're basically, we've seen anything from vertical to just deviated wells, S-bend wells, horizontal profiles. It's obviously going to depend on the surface and downhole constraints as discussed by Colton earlier. I wasn't going to get too much into a lot of the torque and drag and things like that, but we're always making sure we're running our torque and drag models and stuff, making sure that we can get that casing to bottom. The different assemblies that we use, so depending on what we're looking at as far as deviations and things, are our length of our horizontals and things, we're either using a bent motor type of assembly, or else a lot of them will start using the rotary steerable. So one of the benefits of the rotary steerable is you can really control your dips, and you can keep a fairly smooth wellbore to allow us to get our casing to bottom. So basically there's the point the bit, push the bit technologies in rotary steerable. So some of the challenges we've seen in our drilling operations, they're very, very similar to conventional drilling. So pipe sticking, so whether it's differential sticking or key seating, lost circulation. We see a lot of natural fractures, especially at the top of the salt zone. Overbalanced mud, so that's leading to differential sticking. Hole deviation, one of the major issues that we've been seeing with the shallower formations is we just got done a project where basically we for lack of better words, we had to get really aggressive with our drilling assembly in order to deviate the well as much as they wanted in order to hit their bottom hole targets. So we had to dial up our directional assembly in order to get the build rates required to get from the surface to their bottom hole target. Borehole instability, making sure that we keep the mud weights as light as possible. Mud contamination, mud reacting with formation fluids and causing bit balling, things like that. The hole cleaning, we need to make sure we have proper pump equipment and everything, and proper annular velocities and everything to make sure that we're cleaning that hole. Formation damage, reactivity, again, we talk about that reactivity, the bit balling, the water in the mud reacting with the clays and creating balling around the bit. Shallow gas hazards, so shallower gas-bearing zones and H2S zones. So here, you want to talk about this? This, sir.
Yeah, so this is the project that Patrick was just hinting to or alluding to, where we had to get. It was a very directionally challenging project, to say the least. So this facility, what you see on the bottom of the photo, is actually a baseball tee for a Little League stadium. They have basically rented out their surface rights to one. You can see an RV park. This is a high tourist area for fish run and other summer activities. They've also got a Little League baseball stadium. What this is creating issues, though, is getting the salt that's still underneath this facility. If you were to look at, say, the bottom right corner of the photo out of view, there is a wetlands habitat that they've donated to Ducks Unlimited. That is still all their salt that they're unable to get directly on top of and drill down vertically. The salt here is rather shallow, with top of salt being right at 1,700 foot, but their well spacing requirements for the regulator needs 500 foot spacing on surface casing shoes. This unfortunately required kicking off at 140 foot below surface with a 17-inch bit. We had a 3-degree bend on it, and the issue when you start working at directional equipment, one, that large, and two, that aggressive, you start running issues to over torquing situations, blowing bearings on your bit. Anything over 1.5 degree, I would tell you do not need to rotate. You need to keep sliding, but then you're making additional trips to redial your motors. So long-term planning can reduce that. That ultimately drives the cost of your well up, especially on your surface casing with hole that size. And with something that shallow and unconsolidated, typically till you get to hard rock, you're also going to have hole stability issues with it staying open long-term. It's going to want to fall in on you because you don't have the hydrostatic head keeping that borehole open. Along with this project, there was issues with lack of data. They hadn't drilled wells here, let alone collected data within 15 years. In fact, the only people that were still around that had record of it were either working in the plant at the time. No one was over the brine field or had any of the data. It was all paper records, which had consequently been damaged in a flood they had several years prior. So walking into this, it was what I would describe almost a modern day wildcat as far as what to expect and drilling complications because we had no offset reports. On top of the salt, right around 1,700 foot, large natural fracture system. Along with that, there is some heavy swelling clays, the 200 or 300 foot preceding that. One thing we ran into running with a freshwater system on the surface hole is you start getting into your swelling clays. You hydrate these clays and these shell issues, you run into bit ball. And one of the things that a lot of field guys want to do, just for lack of understanding, is they want to mash on it. Well, it's not drilling. My ROP and my torque is dropped way off. Obviously, my bit's not biting the rock or something's going on. So instead of 20,000 pounds, let me stack 30. Well, then let me stack 40 and 50. And what you happen is your cutting structure actually gets covered by the mud and it slicks it up like cake, where you're not cutting, you're not grabbing rock and biting anymore. And as those issues continue to happen and you're not adding clay stabilizers, inhibitors into your system, you start having those issues with mud rings and stuff returning to surface, packing off your flow lines, etc. Except key indicators, if you're drilling fine, your rate of penetration is fine. I like to use mechanical specific energy. It's actually a way you can measure how much energy it's taking to get the rock out of the hole. If all these indicators are going fine, you have a sudden drastic change. Something's changed and not for the better. So decrease in torque and rate of penetration are typically good signs of something's going on at the bit. And ultimately, you got to make a trip. You can sometimes remediate it, downhole pumping like a walnut sweep, kind of sand blasting the bit. But realistically, most of the time you got to trip out and do a change. So with that being said, I'd like to thank y'all very much. And time for the next speaker.